All right, here are the true-false problems from the Unit 2 review packet, and I'll go through these, some of them in more depth than others, but I'll get you what you need out of them, I hope. First one says, if f and g are differentiable, then the derivative, this just means take the derivative of what is in here. Instead of saying dy dx, this is your y value. This is your function, effectively. So take the derivative of f plus g. That is the derivative of f plus the derivative of g. That is true. That's just a basic, you can add and subtract functions. You can add and subtract their derivatives. This one says, if the two functions are differentiable, then the derivative of f times g is the derivative of f times the derivative of g. That is false because you need the product rule. What you would need is derivative of f times g plus the derivative of g times f. Next one says, if f and g are differentiable, then the derivative of f of g of x, that is the chain rule because we have a composition, is equal to f prime of g times g prime. That is true because this is a statement of the chain rule. We've differentiated f, the outside function, leaving the inside function g intact and multiplying by the derivative of the inside function. 4 says, if f is differentiable, then the derivative of the square root of f of x equals this. 5 says, if f is differentiable, then the derivative of the f of the, oh, these are two different. This one is the square root of f of x. This is f of the square root of x. So let's do these down here. Number 4, if I want to differentiate the square root of f of x, that is the same thing as f of x quantity squared. So I need to do a chain rule. So I bring down the 1/2, leaving f of x as my inside function intact, dropping a degree through the power rule for the exponent there, then multiply by the derivative of f. So that gives me, if I simplify this, it gives me f prime divided by 2 times the square root of f of x, which is exactly what they gave us, so this one is true. Now number 5 wants us to differentiate f of the square root of x. So let's see. If I differentiate f of the square root of x, I'm going to go to the derivative of f, leaving the square root of x intact, times the derivative of the square root of x, which is 1 over twice the square root of x. The square root of x, if you recall, is x to the 1/2, and when we differentiate it, we bring down the 1/2 and drop a degree. That's why we have the 1/2, and then the x to the 1/2 is in the denominator. So this, in fact, does match what's here, so this should be true as well. Next, if y equals e squared, then y prime is 2e. That is false because e squared is a constant, and therefore it differentiates to 0. Next, the derivative of 10 to the x. They are using the power rule here. Cannot use the power rule because the base is a number. This is an exponential function. So the derivative of 10 to the x is the ln of 10 times 10 to the x. So this, in fact, is false. 8, very similar to 6. ln of 10 is a number. It's a constant. When you differentiate a constant, you get 0, not 1/10. So this one is false. And then last, number 9, I'm going to have to add in another sheet here so I have plenty of space. So we're taking the derivative of tangent squared, and we're going to take the derivative of secant squared, and we're going to see if they are the same. So tangent squared, first I need to bring down the 2, and I need to drop a degree to a 1. Then the inside function being tangent, I differentiate it to secant squared. Secant squared, I start with the chain rule. I bring down a 2, drop a degree to 1 here, and then the derivative of secant is secant times tangent. So look what we have. We have 2 secants and 2 secants, 1 tangent, and a constant of 2. So this is true. Last 4 questions. Number 10, the derivative of an absolute value function. Frankly, to differentiate an absolute value function algebraically, you'd have to split it into a piecewise, where you'd have, for example, x squared plus x, where x is greater than or equal to 0, and then a negative x squared plus x. I'm not even sure that's the exact way to split this now that I think about it because of this squared. So at some point you have to, there's a split in the domain somewhere in here. My point is that you'd have to write this in two separate equations and differentiate each one and then somehow combine it into the derivative. You can't just do the power rule on what's inside the absolute value. So this is absolutely false. Another way to think about it is the absolute value of x, which graphs as this v, the derivative of the absolute value of x is actually the signum function. So you know that the absolute value of x does not differentiate to 1 because that only applies over on the right-hand side. Okay, number 11, if g of x equals x to the fifth, then if I use here this definition of the derivative, that's what this is. Take the derivative at 2, do you get 80? Well, g of x equals x to the fifth, g prime of x equals 5x to the fourth, so plug in 2, I get 5 times 16, which is 80. So this guy is true. Number 12, this says the second derivative, and this says the first derivative squared. They are not equal to each other. They could be if the second derivative and the first derivative were both 0, for example, but most of the time these are not the same. And then 13 is an interesting one because it says if you have an equation to the tangent line of the parabola at the point negative 2, 4. Well, a parabola has a derivative of 2x. We just do the power rule here, bring down the 2. So I like it that they put in the slope of 2x, and then I like, their y minus 4 and their x plus 2. So this is sort of a standard form here, but they kind of need to plug in the x value of negative 2. Otherwise, you've got this quadratic here. It implies that this x is a variable and can take on any number. So what I would have preferred here is y minus 4 equals 2 times negative 2. It's the slope of negative 4 and then an x plus 2. And that is all.